So in the last class, we were discussing about making an amplifier using negative feedback, an amplifier of gain of more than one. The necessity came because in our experience till now, the only amplifier that we have which has gain of more than one is a common source amplifier. But the not so good thing about a common source amplifier is its gain is dependent on the load. So if the load changes, the gain changes. Again, the gain is also dependent on GM, which essentially means the temperature changes, GM changes, then the gain also changes. So we don't have a very well a stable amplifier which can give you a desired gain, but the gain should remain constant regardless of whatever happens in the world, right? So that type of amplifier we don't have. So that led us to think in a slightly different way. We thought that if we use negative feedback to make an amplifier, then this problem might be resolved. And the argument was a negative feedback loop operates in the principle of observing the output and tweaking something in the loop so that the output remains whatever it is supposed to be. Since it is not an open loop observation, it's not an open loop system. That is, you set the input in some way and hope that the output will settle. In this case, you are observing the output and comparing it with something and taking a corrective action. So which essentially means that you are always keeping the output wherever you want it to be. So if we are successful in making such a loop, then it can be argued that such type of amplifier or such device, if we can make amplifier using such type of negative feedback loops, then it can be argued that it will be stable across process voltage, temperature, or any other ambient changes, right? So while we were discussing this, we developed a very initial framework, and the framework was, if we have to design anything using negative feedback, we essentially need certain things. So one thing is we need to know what our expected output is, right? So we need to know what our actual output is. We need an actual output. I mean, that is kind of obvious. Otherwise, there's no point in making anything. The second thing we need what is our expected output. And the third thing that we need to do is to find out a way of finding out the difference between the expected and the actual output. And that difference we should drive it to zero. If we can drive the difference between the actual output and the expected output to zero, then obviously it makes sense. I mean, the argument naturally follows that the actual output will be equal to the expected output, right? So the actual in a voltage loop, right, where the input is a voltage, output is also a voltage, and we are trying to make a voltage amplifier. Your actual output is maybe V0, the node that you are observing, and your expected output will be some K times Vi, where Vi is the input and K is the amplification factor, where K is more than 1 in this case. And we have to, I mean, with the logic that we have been following till now, the key thing to figure out is what is the difference between the actual and the expected, or expected and an actual, and drive that difference to zero. And the difference in this case is we define it as an error voltage, which is V0 minus K times Vi, and we will drive this to zero. So this driving thing has to be done by us, right? So this has to be designed. So if we have to design a system in which we drive this error to zero. So now then again we saw that there is an inherent problem in this way of formulation, because in order to find out this error voltage, I need access to this K times Vi, and that naturally doesn't exist. If had it existed, we wouldn't have needed a loop in the first place. But the good thing about zero is I can divide both sides by K. So this becomes V0 over K minus Vi tends to zero. If we can realize this and redefine our error voltage like this, then if we make a circuit which satisfies the bottom equation, then also our problem is solved. Now one might turn around and say that if K times Vi is difficult to make, while K times Vi, where K is independent of ambient conditions variation, is difficult to make, then how come V0 over K is not difficult to make? It is not difficult to make because if I have a voltage V0, some voltage V0, and I want to, let's say, reduce the voltage divided by K, where K is greater than 1, means I'm expecting a lower voltage. If I reduce it, for example, if K is 2, then V naught over K is 1 over 2 or V naught over 2. That I can make using a resistor divider, right? So this is V naught over 2. This is a resistor divider. This is way of generating a reduced voltage, which is independent of the values of R, right? So if R changes, obviously the assumption that I am taking is both of these R change in the same way. If both these R's change in the same way, then regardless of whatever happens, this node will always be at V naught over 2. And that is independent of temperature variation, change in weather, change in mood, whatever. It really doesn't matter. It's always V naught over 2. Okay. So as it turns out, this type of, as it turns out, making very well matched resistors is not so difficult in an integrated circuit, because ultimately in an IC you place things very close by. And if you are making these resistors out of the same material, built in the same way, laid out in the same fashion, then it makes sense to argue that one resistor is almost similar to the other. And in fact, that is true to quite a large extent in an integrated circuit, where you can make ratios of less than 1 independent of ambient changes, right? So now we have the setup. And let's assume that I go back to this V naught over K formulation. So if I need V naught over K, then this resistor has to be K minus 1 times R and R, right? So if I, is that correct? R by, yeah. So if I size, let's say I want a gain of, in an amplifier, I want a gain of 3, then all I have to do is to set up a resistive divider in which we have 2R and R, and we get V naught over 3 here. And the next thing is to compare this with the actual input, right? To compare, because what we are doing here, what we are trying to do, we are finding out an error voltage. The error voltage is the difference between the actual input, that is Vi, and V naught over 2, right? So in a block diagrammatic representation, this is V naught over K, and I have Vi. So I need to compare and find the difference, right? In a block diagram, it is easy to compare. I can just put a summer and say this is the error voltage, right? So this is the error voltage, Vi minus V naught over K. One might argue that I can reverse the signs of the summer. Error voltage remains the same, just that the sign might be different, because ultimately I need to drive this V naught over K minus Vi to 0, or Vi minus V naught over K to 0. It doesn't matter from which side I'm approaching, right? So let's take this. We have to start from somewhere. Let's take this sign convention. We'll see what happens if the sign convention changes later on. So now, so we have the error voltage, and we have the output. And again, what we have to do, we have to build something so that based on this error voltage, I take a decision, and the decision will be such that when I drive V naught, VE should go to 0. Right? So essentially what I'm targeting is, I have to put something here. I have to put something between VE and V naught, such that is a decision-making body, right? So here, whatever I'll be putting, this will be a decision driver. This decision driver will be such that it will take the information from VE, because VE is such that we are trying to figure out how to leverage the information of VE and drive V naught. If VE is, for example, if VE is more than 0, right? If VE is more than 0, what should we do? I don't want to, I'm still not asking what should be in the box. What I'm asking is intuitively, let's say is VI is not changing, VI is not in our control, VI is coming from somewhere. If VE is greater than 0, then what should happen to V naught? VE is greater than, how we have defined V naught? Yeah, so if VE is greater than 0, then naturally it means that this voltage is lower than whatever it is supposed to be, which means that V naught is lower than whatever it is supposed to be, which means I have to put something there which has to increase V naught, right? So, and it's the vice versa. If V is less than 0, I have to put something there which decreases the voltage. Okay. So another key thing to note here is that whatever we put here, the input is voltage, output is voltage. So essentially, we are putting something which has a voltage transfer function between input and output. Okay. So the voltage transfer function, let me call it as A or AV, right? Where A can be whatever it is supposed to be. We'll see whatever it is supposed to be. So let's assume that we have a block which has a transfer function AV between VE and V naught. So what I meant to figure out is that what characteristics do we need on AV? If we know that, then we can go and build it. Okay. So let's see. So V naught is VE times AV, where VE is VI minus V naught over K times AV. Fine. So if I write it in, if I jumble all the, if I collate all the same terms together, so this becomes by K V naught over VI becomes, right? Or if I take the K out, or if I simply say this is and is that correct? Yeah. So now we want, what do we want? We want this to be approximately equal to K. This is the expectation, right? So what needs to happen to AV so that this is almost equal to K? Yeah, right. So very large with respect to what? So let's do the, obvious thing first. So if AV tends to infinity, right? So then V naught over VI tends to K. Okay. So now, from our experience, we know that tending to infinity, this type of stuff is it's not possible. But we can make something which is very large with respect to something very small with respect to something. But in this case, we want, when we say that we want AV to be much greater than infinity, should be tending to infinity. What we are inherently saying is that we want AV which is much greater than something, right? What is it we want AV to be much greater than? Is the question clear? So just look at that equation, look at this, and tell me, I want this to be almost equal to K. I understand that AV tends to infinity gives us that, but that's not possible. But what? Yeah, right? So essentially, we want AV to be much. So if AV is much greater than K, then V naught over VI also tends to K. Right? So AV tends to infinity is a difficult thing to do, but AV much greater than K is probably not so difficult, because let's say I am wanting an amplifier which has a gain of 2, 5, 10, maybe something like that. Then I can probably realize an AV which is much greater than 2 or much greater than 10. Maybe if I want much greater than 2, I realize a gain of 20, right? Then I should be able to get a stable gain of K, right? So now so let me pause here for some time and ask and get back to you and ask you whether do you have any particular questions on this, because this is quite fundamental. I know that you are doing 250. Most of the concepts of negative feedback should have been ingrained by now. But what I'll try to do, I'll try to steal some concepts that you already know and mold it in a way that it fits in our course, right? So I need to know if you are uncomfortable with something, if you know something, in a certain way that you want me to emphasize more? Is there anything that you are not comfortable right now with the concept that we are talking about? Everything is very intuitive till now. All good? Okay. Okay, fine. So now the job is to build this AV. So if now, I mean, before you start building this AV, let me throw a question to you. So let's say I want K to be equal to 2. That is, I want V naught over Vi to be equal to 2. Okay. And I say that in this AV, I choose AV to be equal to 10. Some might say 10 is much greater than 2. Let's say it's okay. But I find that I'm unable to make a stable AV, which gives us a gain of 10. Maybe the AV varies between, I don't know, 10 to 20. It varies within the range. Will this suffice? Will this be fine? Or this is a problem? Yes, I agree. Because if, for example, in this case, if AV is infinity, then the output is exactly K, right? If AV is not infinity, so output will have some error. It will not be exactly K. It will be slightly different from K, slightly less, right? But from your experience of using negative feedback, do you think it's a big problem as long as AV is much greater than 1 or much greater than K in this case? So let's do one. So let's find out how much the V naught will vary, right? So can you do this calculation for me and tell me? So I can check from here, right? So V naught over Vi is K times AV by K plus AV, right? We want the expected gain to be equal to K, right? So V naught over Vi ideal should be equal to K. So now what is the error between the actual gain and the realized gain? It's K minus KAV. So which is equal to, oh, something is wrong somewhere. So this goes, so essentially this becomes K times 1 plus AV over K. Right? So now let's say we target a gain of, I mean, so by the way, I mean, again, I'm stealing your concepts from 250. Do you know what this is called? AV over K in the context of this loop? Yeah, it's open loop transfer function or the loop gain. Have you heard of loop gain? Okay, so open loop transfer function or the loop gain. I will cover this in detail, but as long as this open loop transfer function is much greater than 1, or in this case, AV is much greater than K, can you comment on the error? The error is inversely proportional to AB, almost, right? If AB by K is much greater than 1, right? The error is inversely proportional to AB. So error goes down if AB increases, right? So now let me come back to this, right? So if, let's say, we did our calculation and found out that whatever error that we would have had if AB were 10, and now if we change from 10 to 20, do you think the error would have been increasing or it should have decreased, right? So agree that V naught would have changed by certain amount, but if I'm okay with V naught tracking BI with AB equal to 10, I should be happier if AB increases to 20, right? So essentially what we are looking for is a solution in which the AB can change, but as long as it doesn't fall below a minimum, I'm okay. I don't need a precise AB, I need a minimum of AB. Right? So that we can do because a common source amplifier, for example, we can design a common source amplifier whose gain is probably higher than something, but it varies. The variation doesn't remain a problem anymore as long as I can ensure that the gain is above certain value. So that is a much easier proposition than asking somebody to make a precise gain. Okay, so essentially the reason I'm spending time on this is it should be obvious by now is that with the solutions that we have at our disposal, this AV can be a common source amplifier. I can have a common source amplifier in the loop, and with the understanding that the gain of the common source amplifier can vary with temperature, with process, with whatever, but still this negative feedback loop will ensure that P naught is equal to K times Vi, simply because if we can ensure that AV, the gain of the common source amplifier is higher than whatever we need it to be. So you have to over-design the amplifier for sure. So if we are designing a common source amplifier with a gain of 2, the design would have been something. But in this case, if we want a negative feedback loop, and we want a negative feedback loop which gives us a gain of 2, and I want AV to be a common source amplifier, then that common source amplifier needs to have a gain of much greater than 2. Right? So that is a downside. So you need an AV which has a gain which is much greater than the intended closed loop gain. Right? The open loop gain has to be much greater than the closed loop gain in order to get a stable closed loop gain. Okay with that? Okay. Okay. So if that is true, then let's proceed with making this loop with a common source amplifier. So I'll make a, so again, this is all small signal. I'm just biasing it like this. Let me get rid of VDD. Small signal, this is ground. Okay, so now let's pause here for some time and see whether the sense of this loop is correct or not. Right? So when I say the sense of the loop is correct or not, if we go back 5 minutes, what we were discussing was what is expected to happen if VE increases. Right? The loop is supposed to take a corrective action. So if VE increases, what is happening now? What is happening to V naught? If VE increases, V naught is decreasing. So what is happening to this voltage? That is decreasing, right? What is happening to VE then through the loop? It is increasing, right? So this is increasing. So you see the sense of the loop is not correct, right? So if we keep the loop in this format, what's going to happen? It will become unstable, right? It will reinforce whatever is happening. Any disturbance, it is going to reinforce, right? So if because of some noise or something couples to VE increases, or any point in the loop, it increases. Then you see that V naught will decrease. V naught will decrease when it will go through the loop and increase VE, and this will reinforce. The loop can become unstable. Sorry. So, I mean, in a block diagram, it is easy to make things stable. So what is the obvious thing to do? What is an ideal element that I've used here? The transistor is not ideal, resistors are not ideal. What else is there? That summer, that's ideal. We don't yet know, we haven't yet replaced the summer. So I can just say while we are at it, I'll just replace this. Change the sign of the loop, supposed to be stable, right? So I would be surprised how many of us actually do this in reality also. It's like put something, go around and see it's stable. If it's not, just flip the sign, only two options. Okay, fine. So now let's get to, shouldn't put this bubble. I don't know why this bubble keeps coming. So now let's get to designing this this entire contraption. Okay, so couple of things to note. One is a common source. I mean, we have to design this entire thing, and once this is designed, this in the incremental sense, this current is supposed to be Gm times VE or Gm times Vi minus V naught over K, or the other way around, right? The VE now has become V naught over K minus Vi. Right? So if everything works properly, this is what it is supposed to be. But so let's say, let me say that this is, let's only focus on this part. So in a transistor, this current is essentially Gm times Vg minus Vs, right? Trivial stuff. So ultimate goal is to get rid of that ideal summer, right? So can I do something to ensure that this current that is coming out from the common source amplifier in the circuit on the top is the same as whatever it is supposed to be? If I look at this current equation in the bottom, what should I connect to what? Okay, maybe I'm confusing you. So let me ask you this way. So let's say I manufacture a way somehow to ensure that this voltage is V naught over K and this voltage is Vi. Then can I get rid of the summer? So this will be then V naught over K minus Vi, right? So looks like this current, whatever it is coming out, will be same as whatever I need. Correct? So in that case, I can probably get rid of the sum. Yes, we can do that, but there is an issue. The issue is the following. So in a common source amplifier, when I am driving some input to the gate does not load the input, right? So let's say I have one input here, Vi1, Vi1. It has some RS. So this voltage will be Vi1. The gate does not load. But if I have another input, Vi2, it also has an RS, or it need not be the same RS, let's say RS1, RS2. So this will naturally draw current and it will load, right? So this voltage will not be same as Vi2. Okay, so that's why directly connecting V naught over K to here and Vi to be here might not be a good solution all the time because of the loading effect. Okay, so which essentially means that we have to, one of the terminals is fine, one of the terminals is going to the gate, not an issue, but the other terminal cannot be the source. If the other terminal is the source, then you will draw current through from the source to from the whatever you are supposed to be driving into the source, and naturally the voltage will get disturbed. So we cannot use it directly. So what other options do I have? So So let's forget about the loop thing for the time being. The problem statement has now become different. The problem, or rather, problem statement has become slightly modified. So we know that I want this, but in order to get this, I need to apply one input to the gate and other input to the source. Connecting to the gate is not an issue, but connecting to the source is an issue. Right? So I want to address that problem first before I go back to the loop again. So what I'm asking is, I need a solution in which I need a contraption which can accept two inputs, right? And it will give me the same output of that of a common source amplifier, but without the additional headache of loading. Okay. So again, so this is Vi. Let's say this is V1, Vi1, and I have another input Vi2, and all of them have a resistance associated with it. I don't want to connect it here. I want to connect it in such a way that no current flows from Vi after the connection has been made. So essentially what I'm asking is, I need to put a contraption here, right, which can help me buffer the voltage Vi2 into the source of this transistor M1. Note that, okay, before I tell you what to note, can you tell me what are the characteristics that you are looking for in this contraption? One, no current flows. In terms of input impedance, output impedance of this contraption, what do you expect the input impedance to be? Ideally. Yeah, much greater than something. Ideally, it should be infinity. Right? So again, think of the control sources. So if you know the input impedance, what it's supposed to be, it has to be a voltage control in this case, right? Voltage controlled contraption. Now, voltage, you can have two options: voltage control voltage source, voltage control current source. Right? So now I have to turn our attention to the output side. So here at the output side, what am I expecting? I'm expecting this guy, this Vi2, to be appearing here, right? Or a part of the Vi2 to be appearing here, regardless, right? So, but note that I'm not looking for a gain here. Right? I mean, even a gain of 1 is fine. Gain of slightly less than 1 probably might also be fine. So can you think of an architecture among all the things that we have done till now, which can give us this voltage buffering? Common source, common drain, common gate, then all the other fancy architectures, some of them that we have done. Common drain, right? A source follower, right? If you recall, if I have this, and even if I have some RL here, so if this is Vi, this voltage was almost equal to Vi, or I mean, need not be almost equal to. This voltage was Gm Vi RL by 1 plus Gm RL. Right? So if as long as we can ensure that this output resistance, which is 1 over Gm, is much less than RL, this behaves like a voltage buffer. Right? So if you recall, we had done this multiple times, and also there were assignments on this. So it essentially means that I have to replace this with a voltage buffer. So let me replace this guy with a voltage buffer. And I'm drawing everything in incremental domain. So I'll not connect anything to the for the biasing purpose. We'll do the biasing later, but everything is in incremental mode. So if I do this and I say that this is M2, right? So let's assume this has a transconductance GM1, this has a transconductance GM2. Can you calculate what will be the incremental current to this? So this is Vi1, this is Vi2. I want the incremental current through GM1. This is the incremental picture. Can you please calculate and tell me? So this voltage, I mean, the easiest way to go about doing this is break it down into small impedances. So I can say that this impedance looking up is 1 over GM2, right? Looking into the source of M2. So this voltage here is, I mean, I'll basically use the same formula that I had here. So that voltage will be GM1 over GM2 by 1 plus GM1 by GM2. When I am doing, when I have input VI1, right? If I have VI2, basically I'm using superposition, then I will have GM2 over GM1 by 1 plus GM2 over GM1. So this will become GM1 VI1 plus GM2 VI2 by GM1 plus GM2. So this will be this voltage, let me call this Vx. If I know Vx, then I know the current, this current I1. So that current I1 will be GM1 VI1 minus Vx, which will turn out to be GM1 GM2 by GM1 plus GM2 times VI1 minus VI2. Right? So if you do the math, this is what you are going to, this is what you are going to see. Okay. So a very important result. So you should pay some attention to this result, because now what we are seeing a contraption. Let me redraw the contraption. Again, I'll emphasize that this is all in the incremental domain. So this current, so I call this I1. This I1 is equal to, or rather let me say, is proportional to VI1 minus VI2, where the proportionality constant is GM1, GM2 by GM1 plus GM2. In a common source amplifier, for example, and let's say if I were to apply VI2 here directly, this current, so I would have called this I1B. This I1B also would have been proportional to VI1 minus VI2, and the proportionality constant would have been GMB, or GMB times VI1 minus VI2. Right? So you see that these two contraptions behave quite similarly with respect to each other with regards to the incremental current that it is generating. Just that the value of the conductances transconductance are different. In this case, the value of the transconductance is GM1, GM2 by GM1 plus GM2. But in the other case, the value of the transconductance is the transconductance of the MOSFET itself. Right? So one might argue that all the things that we see in a common source amplifier, we should also be able to see in this contraption. Right? But the key difference is in this case, the input is not being loaded when you are attaching the input to the gates of M1 and M2. However, in this case, VI1 was having the benefit of not being drawn any current from, but VI2 was not. Right? If VI2 is sensitive to current being drawn from its sources, I mean, obviously, if you have an ideal voltage source, there is no problem. But always you will not have ideal voltage sources. So there will be a series resistance with VI2. So you will not get the benefits of often high input impedance contract. However, in the second case, you get it. Okay, so that is the key difference. Otherwise, more or less, it's kind of similar. So often this type of contraptions are called a common source amplifier loaded with a common gate amplifier, right? So if you look at it carefully, and look at it from the perspective of M1, the load, the stuff that is connected to the gate to the source of M1 is I mean, if I disregard that Vi2 has been Vi2 is a voltage source, let's assume Vi2 is 0, then it looks like a common source amplifier has been loaded with a common gate contraption, right? So this seems to be a common gate. You are pushing current into a current controlled current source kind of contraption. You are pushing current into the source of M2 and taking it from the outside, right? So another key point to note here is incrementally, this current I1 is going to flow into M2, but in the opposite direction. When the incremental current is going, there's no other place for this incremental current to go. So once you know the incremental current in M1, you also know the incremental current in M2, but just that the directions are different. The incremental directions are different. Okay, make sense? Doesn't make sense? Questions? Confusions? Okay. So then the time has come to replace this contraption into the loop. Now that we have a contraption, we can apply both the inputs. We can replace this contraption into the loop, and let's do that. So again, let me redraw the loop. So we were trying to get one of, so this voltage is V0 over K minus Vi. So we are trying to get rid of the summer, and we saw that getting rid of the summer meant we have to connect something to the source of the transistor. That was a problem. So we manufactured a contraption which can buffer the input and connect it to the source of this transistor M1. So we are going to use that contraption here. So this was M1. This will be M2. So let's connect Vi1 here and V0 over K here. I mean, if M1 and M2 are identical, then really doesn't matter which side you connect, but the next thing will matter. So let's, I need to take the output. So in case of a common source amplifier, we had this, right? So let's do the same thing, keep the same thing as is, because ultimately the thing was we wanted to get everything from a common source amplifier. So this current here will be what? GM, whatever the effective GM, right? So GM1, GM2 by GM1 plus GM2 times Vi1 minus V0 over K, right? So now let's compare this with respect to what we want. So let's take the output V0 and then generate this V0 over K. Okay. So this we connected up and everything fine, but we need to also figure out whether the sense of the loop is right? Just the way we argued in the circuit in the loop in the top, if the sense of the loop is right or not, we have to argue the same thing here. Okay. So how do we figure out if the sense of the loop is right or not? We essentially we assume that one of the elements in the loop, one of the voltages in the loop has increased. We go around the loop and see if the loop is reinforcing that increment or pushing the increment in the other direction, right? So let's do that. So let's assume V0 has increased. I have not changed VI1, VI2, nothing has changed, right? But for some reason, let's assume V0 has increased. So what will happen to V0 over K? V0 increases, so V0 over K increases. So what if V0 over K increases? What can you comment on this voltage? Again, don't disregard VI1, right? So let's assume VI1 is incrementally grounded. So if V0 over K increases, what can you comment on that common node? Increase, decrease sound similar. So goes up, goes down. Goes up. Okay. Goes up. Good. Then what happens to this voltage? So you can figure it out from the current, right? If that the voltage, if Vx goes up, this is Vx. If Vx goes up, what happens to the incremental current? Let's say I'm talking about the incremental current, okay, in the direction that I have seen. The incremental current decreases in the direction that has been shown. So what happens to this voltage? Goes up, goes down, goes up, right? Okay. So this goes up. So eventually, you see, I had pushed this voltage up, and the loop is also trying to push the voltage up, right? So it's like a reinforcing. It's almost like a positive feedback loop, right? So it's reinforcing a disturbance. So this loop will eventually go up, I mean, will become unstable. Okay, so now what is the problem? The problem is the signs of the loop are not correct. It's equivalent to saying here, right? So we had positive, negative. We flipped the sign and it was fine. So in this case, how do I flip the sign? So obviously, flipping the sign is a difficult thing to do in this case, but I can simply say that instead of connecting V0 over K here, I can connect V0 over K here. And instead of connecting VI here, I can connect the VI here. That's equivalent to flipping the sign. And that is in our control, that I can always do. I can do, I mean, instead of writing this, all this messy stuff, I can then simply say that if I connect that, that is equivalent to saying that is equivalent to saying I connect the resistor here and connect it here and don't change anything else, right? That's it. I not name that. It is equivalent to saying that, right? I flip the input terminals, or I don't take the output from one, I take the output from the other, right? So if I do this, then I go around the loop and I see that the sense of the loop is correct. Okay, so this is so we'll stop here. We'll meet on Monday, I guess. So we'll continue from here. But before I end, let me give you a jargon. So this stuff that you see here is often abbreviated as an operational amplifier or an op-amp, right? An op-amp is nothing but an op-amp with negative feedback loop is nothing but some bunch of transistors put together, friends. And you have used this multiple times in ESC 201, and we are going to build it in the next few classes. Okay, it's essentially a common source amplifier, right? So put in certain fashion.